Hello, today we'll be doing a 1990 APC physics problem. If you read the question, it states, in the mass spectrometer shown above, particles having a net charge positive Q are accelerated from rest through a potential difference in region 1, which is this area. They then move in a straight line through region 2, which contains a magnetic field B and an electric field E. Finally, the particles enter region 3, this final portion, which contains only a magnetic field B, and move in a semicircular path of radius r before striking the detector. The magnetic fields in region 2 and 3 are uniform, having the same magnitude B, and are directed out of the page as shown. In the figure above, indicate the direction of the electric field necessary for the particles to move in a straight line through region 2. So you can approach part A in two ways. The first being the right-hand rule, which you point your pointer in the direction of velocity. You point, first you choose the right hand, sorry, that's my left hand. So you point your index finger in the direction of velocity, and you point your middle finger in the direction of the magnetic field, which is directed at us. So it's like that. And then your thumb is directed towards the electric force. So if the electric force is going down, then the field is going to go up, as shown here, because the field lines always go from positive to negative. Another way to think about it is that here the electric field in region 3 is removed, which forces the particle to go down. So in region 2, where there was an electric field, it must have been pushing the electron up. Well, not the electron, the particle. And so for part A, you simply have to draw arrows pointing up in region 2. Now, the next part say, in terms of any or all quantities Q, B, E, and R, determine expressions for B, the speed V of the charged particles as they enter region 3. So, Q, E is equal to QVB sine theta. And because they're perpendicular, sine theta goes away, and we're left with QE is equal to QVB. The Q's cancel, and V is equal to E divided by B. Sorry, I should be consistent with whether my letters are capital or lowercase. And that's part B. Part C asks for the mass m of the charged particles. So we can use the formula for centripetal force, which tells us that mv squared divided by r, in this case it's capital R, is equal to the force, which is QVB. We need to isolate the m, so we first can cancel out the velocities and get mvr equals qb. And then m is equal to r, rqb divided by v. We figured out v in part B, it's E over B, so once we plug that in, we get that m is equal to b squared times r divided by E. And that's basically it for part C. Oh, sorry, forgot the key. Okay. Part D asks us for the accelerating potential V, capital V, in region 1. Because mv squared over r is centripetal force, we know that if we're looking for centripetal acceleration, we just have to remove the mass and we get v squared over r. In this instance, we found v before. We found v before, right? So the acceleration is simply equal to v squared over r. I already stated that, and then v is equal to the potential v in region 1 is going to be equal to er over 2. Now we can move on to part E. Part E asks us for the acceleration a of the particles in region 3. So a is equal to e squared over b squared r. This is just basically using, sorry, I should expound on this. mv squared divided by r, we get rid of the n. We found v squared here, that's e squared over b squared, and we add in the radius, so that's r. And then part F asks us for the time required for the particles to move along the semicircular path in region 3, so they want the time. We know that speed is equal to distance over time, so time is going to be equal to distance over speed. In this instance, the distance is half of a circle, a semicircle, so it's 2 pi r divided by 2 divided by speed, which is e over b. We cancel out the 2's, and ultimately we get pi rb over e. And this is part F. I'm not happy with part D, so I'm going to redo it because I don't think I explained it well. So part D is asking for the accelerating potential V in region 1. Work is equal to QED, which is equal to QV, and we're looking for this potential, as opposed to the acceleration, which I incorrectly stated before. And QV is force, so that's equal to 1/2 mv squared, not force, energy. So these are both energy equations, so we can set them equal to one another. V becomes equal to m. We substitute the velocity in, it's m over e squared divided by 2 cube b squared. And we found what m was equal to in part C. This is m. So we plug that in for m because we're not allowed to use mass. And if you do that, qrb squared divided by e times what we had, e squared divided by 2 b squared. Once again, I'm not being consistent with the variables, I'm sorry about that. You cancel everything out and you get v is equal to er over 2. And with that, we have successfully completed this free response. Thank you.